Lesson 11.6 is all about recursion and special sequences. Now, before we can talk about those, we need to review some of our older ideas. So if we have n in our sequences, n is the number of terms. So then if we were looking at a sub n, that would be the nth term that we're looking at. So for example, a sub 3 is our third term. So let's say we had a sub n sitting out in the middle here. We're not exactly sure which one we have, but we know that there could possibly be other terms around it before and or after our a sub n. So let's just pretend that we had a sub 4 was our a sub n, which means the next one right after it would have to be a sub 5. So in terms of our n, we would call it a sub n plus 1. It's where we started, add another one. That gets us to a sub 5. Then the next one would be a sub 6. So in terms of n, we'd have to call that a sub n plus 2. It's the one 2 after where we started from. Going in the opposite direction, we'd have a sub 3 and a sub 2, the ones that are right before our a sub 4. So in terms of n, we call it a sub n minus 1 and a sub n minus 2. And they would all be a part of this one larger sequence. Now that we kind of have the ideals of our terms down, I want to show you a picture here of what's known as the Fibonacci spiral. Notice how each of these kind of start in the middle and spiral all the way out, growing, getting larger as they go. So in this case, we had a seashell. Over here, it looks like an ear. This is an image of how an ear looks. This is a hurricane, how weather patterns look and naturally appear. Here we have a rose petal, or a rose, and you can notice how the petals, as they grow and expand, they kind of create this spiral effect. Now, why did we look at that? Again, like I said, that is the Fibonacci spiral. That comes from the Fibonacci sequence, which is if we start with two values of 1 and 1, and if we were to add those together, 1 plus 1 is 2. Now, if we were to add 1 and 2, we would get 3. If we were to add 2 and 3, we would get 5. 3 and 5 make 8. 5 and 8 make 13. 8 and 13 make 21. 13 and 21 make 34, and so on. These numbers, this sequence, is where the Fibonacci spiral came from. If we start here with a small square of 1 by 1, and another 1 by 1 square, and just go from corner to corner, then add a square that has sides of, it's 2 by 2, then a 3 by 3. I should do this in a different color. 3 by 3, 5 by 5, 8 by 8, 13 by 13, and so on. This creates our Fibonacci spiral. And it all came from these numbers, the Fibonacci sequence. So we can see how math is applied to real life, especially in nature. It happens naturally occurring. Humans didn't create it. It was already there, applying by the rules of math. So that Fibonacci sequence is what we would call a recursive formula. It was all based on the one before. And by that I mean, if we called 3 right here our a sub n equals, it was 2 plus 1, so it would be a sub n minus 1 plus a sub n minus 2. That was the way to find our a sub n. Same thing if we were looking at 8 was our a sub n. It was a sub n minus 1 plus a sub n minus 2. It's always the 2 before it added up. That's how a recursive formula works. Recursion is basically when you're taking terms, adding up from the previous terms to get your new one. So here's an example of how it looks, or how it should appear. If we start with a sub 1 equals 5, and we're looking for the first 5 terms. So 1, 2, 3, 4, 5 terms, starting at a sub 1 all the way through a sub 5, and we are given that a sub 1 is 5. We have the formula in that a sub n plus 1 is 2 times a sub n plus 7 for every n that is greater than or equal to 1, which means this part just means we continue to get bigger continuously. And we can't go this way at all because it's only for the n's that are greater than or equal to 1, but we just continue to go bigger in this direction. So what is this formula actually saying? Well, it's saying that the term that we're looking for, our n plus 1, equals 2 times our previous term, and then add 7. So if our previous term was 5, we need to take 2 times 5 and then add 7 to get our new term. So that would become 17. To get our third term here, we would do 2 times 17 plus 7. Okay, 2 times 17 is going to come out to 34, plus 7 is 41. And again, for our next term, 2 times 41 plus 7, so that would be 82, plus 7 is 89. And then this last one would be 2 times 81, again, still plus 7, so that would come out to 162, plus 7 is 169. So this would be our series, or our recursive series. Moving on from there, iteration. When we iterate a function, that's basically just saying it's a function using its own terms. And it does that over and over. And I'll show you what that means here. If we are given our function notation, and we start with our x sub o, and we want to find our first three iterates, x sub 1, x sub 2, and x sub 3. And we know that the x sub 0 equals 5. Then to find our next one, we have to plug it back into our formula. So we would say the next piece is going to be f of 5 equals 3 times 5 minus 1. So we're just plugging our 5 from here into our formula. 3 times 5 is 15, minus 1 is 14. So 14 is going to be our next term here. Next, we would be looking for f of 14 as our third term. So we'd say 3 times 14, then minus 1. 3 times 14 is 42, then minus 1 becomes 41. Same thing for our last piece then. We need to do f of 41, which equals 3 times 41 minus 1. To find our last piece, 3 times 41 is 123, minus 1 becomes 122. And so that's how we'd find our first three iterates of the function, given our value x sub 0. And you could continue that on to find the next ones, but that's how you would find an iterate. So with that, stay golden.